Hello viewers, in today's session we are going to discuss another important and conceptual problem from increasing and decreasing functions. And in this session we are going to discuss this problem where we have to find the intervals in which the function f of x which is equal to x minus 1 square times e raised to minus x, and we have to find the intervals where this function is increasing and decreasing, right? So let us see how we can make use of the concept of derivative to find out the intervals where this function is increasing and decreasing, right? So let us first take the definition of increasing function and decreasing function in terms of derivatives. Now consider a function, say y is equal to f of x, which is defined in some domain D, right? And here this function is said to be an increasing function if the derivative, that is f prime of x, is greater than and equal to 0 for all x belonging to the domain, right? And the function is said to be a decreasing function if f prime of x, that is the derivative, is less than or equal to 0 for all x belonging to the domain, right? So if the derivative is greater than or equal to 0 for all values of x belonging to the domain, then this function is said to be an increasing function. And if the derivative is less than or equal to 0 for all x belonging to the domain, then the function is said to be a decreasing function, right? So here we are going to make use of these two definitions to find out the intervals where this function is increasing and decreasing. So let us first find out the derivative of f of x using the product rule, because here we have the product of two functions. Suppose this function is u and this function is v, then we have f of x as a product of two functions of x, that is x minus 1 square, and e raised to minus x, which is an exponential function, right? So we know that the product rule for the derivative of the product of two functions is given by v times derivative of u. Then we have u times a derivative of v, right? So here f prime of x is given by d by dx of x minus 1 square e raised to minus x. So applying this rule, we have u is equal to x minus 1 square, v is e raised to minus x. So we have e raised to minus x, and then the derivative of x minus 1 square. Then we have x minus 1 square, and here we have the derivative of e raised to minus x. So here the derivative of x minus 1 square is given by 2 times x minus 1 using the power rule, and then by chain rule the derivative of x minus 1 is simply given by 1. The derivative of x is 1 and the derivative of 1 is 0, and here we have x minus 1 square, and the derivative of e raised to minus x is given by negative of e raised to minus x. So now here we can now take e raised to minus x and x minus 1 as a common, right? So we have the common factor e raised to minus x and x minus 1. So we have now inside the bracket we have simply here 2, and then here we have the negative sign here, and we have x minus 1, right? So we can now write e raised to minus x, x minus 1, and here we have minus x plus 1, so this is 3 minus x, right? So now if we write this expression as taking negative 1 common, then we can also write it as negative of e raised to minus x, and here we have x minus 1, and here we have x minus 3, right? So now the derivative of the given function is given by negative of e raised to minus x, and here we have x minus 1 and x minus 3. So we can also write it as negative of x minus 1, x minus 3 over e raised to x. So now this function is said to be an increasing function if we have f prime of x is greater than or equal to 0. And here we have f prime of x as negative of x minus 1. Then we have x minus 3, and here we have e raised to x, and this is greater than or equal to 0, right? So now see, here we have a negative of x minus 1 times x minus 3 divided by e raised to x, right? So this entire quantity is greater than or equal to 0, right? So now here in the denominator we have e raised to x, and e raised to x is always going to be greater than 0 for all x belonging to the set of real numbers, because the exponential function is always going to be greater than 0 for all x belonging to R. So here this quantity is to be greater than or equal to 0 only when this expression, that is x minus 1 times x minus 3, is less than or equal to 0. Because when this product, that is x minus 1 times x minus 3, is less than or equal to 0, then this entire quantity is greater than or equal to 0, because here we have a negative sign, right? So when here we have e raised to x greater than 0, right? So the denominator is always going to be a positive, that is it is greater than 0 for all x belonging to R. So this quantity, for this quantity to be greater than or equal to 0, this product has to be less than or equal to 0, that is this product has to be negative, because when this product is negative, then here we have a negative sign. So when negative sign is multiplied with the negative sign, then it becomes positive, and in that case this entire quantity is greater than 0, right? So this product has to be less than or equal to 0, that is this product has to be negative. So now in other words, we can say that here we have a negative sign, right? And if this product is less than 0 or equal to 0, that is if the product x minus 1 times x minus 3 is negative, and in the denominator e raised to x is always going to be positive, right? So here we have positive. So when we multiply these two negative signs, then we have positive, and in the denominator we have positive, and this entire term is positive. So this is greater than or equal to 0. So the condition for this entire term to be greater than or equal to 0, this product x minus 1 times x minus 3, it has to be less than or equal to 0. So now we have to solve this inequality, right? So this inequality is of this form, that is x minus alpha times x minus beta less than or equal to 0, where alpha is equal to 1, and beta is equal to 3, and alpha is less than beta, right? So whenever we have an inequality of this form, then the solution of this type of inequality is given by x greater than or equal to alpha but less than or equal to beta, right? So here alpha is 1 and beta is 3. So the solution of this inequality is given by x greater than or equal to 1 and less than or equal to 3, right? And we can also write it like this: x belonging to the closed interval 1 to 3, right? So this function is an increasing function when f prime of x is greater than or equal to 0, and here we have obtained this interval x belonging to the closed interval, both the endpoints are included. So when x belongs to this closed interval 1 to 3, then this function is an increasing function, right? Because from here, if we find out the critical points of the function f of x, then we must have f prime of x is equal to 0. So when we take f prime of x is equal to 0, then we have minus x minus 1, x minus 3 e raised to x equal to 0. So here e raised to x cannot be equal to 0 for any value of x belonging to R. So this product has to be equal to 0. So we have x minus 1, x minus 3 is equal to 0. So from here we have x is equal to 1 and x is equal to 3, that is x minus 1 is equal to 0 and x minus 3 is equal to 0. So here we have the two critical points of this function f of x, that is 1 and 3. So here we have the real number line, here we have minus infinity, here we have plus infinity, and the critical points are 1 and 3, right? And this function is an increasing function in this interval x belonging to 1 to 3. So here in this region, the function is an increasing function, right? So now for f of x to be a decreasing function, we must have f prime of x is less than or equal to 0. That is a negative of x minus 1 times x minus 3 over e raised to x is less than or equal to 0. So now again we'll apply the same argument here. Here e raised to x is greater than 0 for all x belonging to R. So this quantity is always going to be a positive, right? So now for this entire term to be less than or equal to 0, this product, that is x minus 1 times x minus 3, must be greater than or equal to 0. So in this case, this product has to be a positive one, because here we have already a negative sign. So here we have a negative sign due to the derivative, and here if this product x minus 1 times x minus 3 is greater than or equal to 0, that is if this product is positive, and in the denominator we have a positive quantity. So here negative times positive is negative, and in the denominator we have a positive quantity. So this quotient is going to be a negative one, right? That is this entire term is less than or equal to 0 when this product is positive, right? So for f prime of x to be less than or equal to 0, this product should be a positive quantity, right? So now we have to solve this inequality. So now to solve this type of inequalities which are of this form, x minus alpha times x minus beta is greater than or equal to 0, where alpha is less than beta. Here alpha is 1 and beta is equal to 3. And the solution of this type of inequality is given by x belonging to the interval that is from minus infinity to alpha, and then we have the union, and here we have beta to a positive infinity, right? So the solution of this inequality is given by x belonging to minus infinity to alpha. Alpha is 1, and here we have the union, then beta is 3, and here we have plus infinity, right? So this function is a decreasing function when x belongs to minus infinity to 1, union 3 to infinity, and here we can represent this interval on this real number line. So from here minus infinity to 1, right? So here we have this region, right? So minus infinity to 1, and then we have 3 to infinity. So from here 3 to infinity, right? So in this interval minus infinity to 1, union 3 to infinity, we have the function as a decreasing function, and from 1 to 3 we have this function as an increasing function. So the required intervals are given by this closed interval 1 to 3. This is for increasing function, and minus infinity to 1, union 3 to infinity is for decreasing function. So this is how we can find out the intervals where this function is an increasing function and a decreasing function. Hello viewers, in today's session we are going to discuss another important and conceptual problem from increasing and decreasing functions. And here we are going to solve this problem where we have to find the intervals in which the function f of x, which is equal to x minus 3 times the exponential function e raised to minus 2x, is increasing and decreasing. So we have to find out the intervals where this function is increasing and decreasing, right? So to get the intervals, let us first find out the derivative of this function, right? So f prime of x is given by d by dx of x minus 3 times e raised to minus 2x. So here we have to make use of the product rule for a differentiation. That is, if we have the product of two functions of x, say u and v, then we have v times the derivative of u with respect to x, then we have here u times the derivative of v. So here we can take x minus 3 as the function u, and this function as v. So we have the derivative, that is e raised to minus 2x times the derivative of x minus 3, then we have x minus 3 times the derivative of e raised to minus 2x. So here we have e raised to minus 2x, the derivative of x is 1, derivative of 3 is 0 because this is a constant function, and then we have x minus 3 times the derivative of e raised to minus 2x. So here the derivative of e raised to minus 2x with respect to x is e raised to minus 2x, and then by chain rule the derivative of minus 2x is simply minus 2 because the derivative of x is 1, right? So here we have now simply e raised to minus 2x times 1 is e raised to minus 2x, and here we have minus 2 times e raised to minus 2x, and then we have x minus 3. So now we can take e raised to minus 2x as common. So here we have 1 and then we have minus 2 times x minus 3. So we can now write e raised to minus 2x, and here we have 1 minus 2x plus 6, and this is e raised to minus 2x, and here 6 plus 1 is 7, so we have 7 minus 2x. So the derivative of this function, which is the product of two functions, x minus 3 is a polynomial function and this is an exponential function. So we have the derivative that is equal to e raised to minus 2x times 7 minus 2x. So now we can also write this derivative as 7 minus 2x over e raised to 2x. So now let us find out the critical points of this function. So the critical points can be obtained by equating the derivative equal to 0. So we have 7 minus 2x over e raised to 2x is equal to 0, and we know that e raised to 2x is not equal to 0 for any value of x belonging to the set of real numbers. So the denominator cannot be equal to 0, so we must have 7 minus 2x is equal to 0. That is, the numerator should be equal to 0. So from here we have 7 is equal to 2x, that is x is equal to 7 over 2. So this is the critical point of this function f of x, where the derivative is equal to 0. So now for increasing function, we know the condition, that is f prime of x must be greater than or equal to 0. So a function f of x is said to be an increasing function in its domain if the derivative is greater than or equal to 0, right? And if we take the function as, say, y is equal to f of x, which is defined in some domain D, then the function is said to be an increasing function if dy over dx is greater than or equal to 0 for all x belonging to the domain. So here for increasing function we must have this condition. So now f prime of x is given by 7 minus 2x over e raised to 2x, and this is greater than or equal to 0, right? Now see here, the denominator, that is e raised to 2x, is always going to be greater than 0 for all x belonging to R, right? So the exponential function is always going to be greater than 0 for all x belonging to R. So for this quantity to be greater than or equal to 0, the numerator, that is 7 minus 2x, it has to be greater than or equal to 0. So now we can easily solve this inequality. This is the linear inequality. So we have minus 2x greater than or equal to minus 7, right? So now multiplying both sides by -1, we have here positive, here also we have positive, but the direction of the inequality, it gets reversed, right? And now dividing both sides by 2, we have here 2x over 2, here we have 7 over 2. So now we can write x is less than or equal to 7 over 2, right? So here we have the real number line minus infinity, here we have plus infinity, and the critical point is 7 over 2, right? So when x is less than or equal to 7 over 2, then this function is said to be an increasing function, right? So x less than or equal to 7 over 2 can also be written as x belonging to the interval minus infinity to 7 over 2. So this is the interval where this function is an increasing function. So now for decreasing function, we must have the condition, that is f prime of x must be less than or equal to 0. And if we take this function y is equal to f of x, which is defined in some domain D, then the function is said to be a decreasing function if we have dy over dx less than or equal to 0. So here f prime of x is given by 7 minus 2x over e raised to 2x less than or equal to 0. So now again we can apply the same argument here. E raised to 2x is always going to be greater than 0, right? So here we have 7 minus 2x divided by e raised to 2x is less than or equal to 0. So the denominator is already greater than 0. So for this term to be less than or equal to 0, the numerator, that is 7 minus 2x, it must be less than or equal to 0, right? So here we can solve this inequality as we have done in this case. So we have minus 2x less than or equal to minus 7. Now multiplying both sides by negative 1. Here we have positive 2x. Here we have positive 7. But the direction of the inequality gets reversed. And now dividing both sides by 2. Here we have x and here we have a 7 over 2, right? So this function is a decreasing function when x is greater than or equal to 7 over 2. That is x belonging to the interval that is 7 over 2 to positive infinity, right? So these are the required intervals where this function is increasing and decreasing, and 7 over 2 is the critical point of this function f of x, right? So from minus infinity to 7 over 2, we have the function as an increasing function, and from 7 over 2 to infinity we have the function as decreasing function. So this implies that when we take this interval, then the derivative is always going to be greater than or equal to 0. And when we take this interval, then the derivative is always going to be less than or equal to 0, right? So this is how we can find out the intervals where this function is increasing and decreasing. Hello viewers, in today's session we are going to discuss some important problems from increasing and decreasing functions. So here first of all we'll take this problem where we have to prove that the function f of x, which is equal to x minus 1 over x, is increasing for all values of x belonging to R, where x is not equal to 0, right? So here the domain of this function is given by the set of all real numbers excluding x is equal to 0. So now here this function is not defined for x is equal to 0, right? Now from the definition of increasing function, we know that a function f of x is said to be an increasing function if the derivative, that is f prime of x, is greater than 0 for all x belonging to the domain of the function, right? So a function f of x is said to be an increasing function if its derivative is positive for all x belonging to the domain. So here let us first find out the derivative of this function. So f prime of x is given by d by dx of Here we have x minus 1 over x. So we have the derivative of x is 1, and the derivative of 1 over x is given by minus 1 over x square. So this is now 1 plus 1 over x square. So the derivative of this function is 1 plus 1 over x square, right? So here we see that 1 is positive, and this term, that is 1 over x square, is always going to be greater than 0 for all x belonging to R, where x is not equal to 0, because x square is always going to be greater than 0, right? So this entire term, that is 1 is positive, 1 over x square is also positive, so the sum of two positive numbers is always going to be greater than 0. So we have now f prime of x is greater than 0 for all x belonging to R, where x is not equal to 0. So the derivative is positive for all values of x belonging to R, where x is not equal to 0. So this shows that this function is an increasing function for all x belonging to R except x is equal to 0. So now consider this problem where we have to prove that the function f of x, which is equal to sine x minus cosine x, is an increasing function on this interval, that is minus pi by 4 to pi by 4, right? So here what we will do, we'll first find out the derivative of this function. So f prime of x is equal to d by dx of sine x minus cosine x, and the derivative of sine x is cosine x, and the derivative of cosine x is minus sine x, and here minus multiplied with minus, it becomes positive, so we have cos x plus sine x. So the derivative f prime of x is given as cosine x plus sine x, right? Okay, so now here what we can do, we can apply some trigonometry to this function, that is cosine x plus sine x. So here the derivative is the sum of cosine function and sine function. So let us convert this function into a sine function only, right? So for this, what we can do, we can write here square root of 2, and then we can write here 1 over square root of 2, and here we have cosine x, then here we can also write 1 over square root of 2, and here we have sine x. So what we have done here, we have multiplied this term by square root of 2, and then here we have written 1 over square root of 2 times cosine x, then here also we have 1 over square root of 2 times sine x, right? So here the purpose of expressing this term like this is to replace this 1 over square root of 2 by sine pi by 4, right? And here we can replace 1 over square root of 2 by cosine pi by 4, because sine pi by 4 is equal to 1 over square root of 2, and cosine pi by 4 is equal to 1 over square root of 2. So now here we can now write square root of 2, and 1 over root 2 can be written as sine pi by 4. Then here we have cosine x, and then here we write cosine pi by 4, and then we have sine x, right? So now this expression is of this form, that is sine a cosine b, then we have cosine a and sine b, right? So the purpose of writing this expression like this is to convert this expression into a sine function only, right? So here a is pi by 4 if we compare both these expressions, and b is equal to x, right? So now this expression is the sine formula for sum of two angles. So we have sine a plus b. So this expression is now square root of 2, and here we can now write sine a plus b. A is pi by 4 and b is x, right? So now we have expressed the derivative f prime of x as square root of 2 times sine pi by 4 plus x. So now here we are given this interval, that is we have to prove that this function is an increasing function in this interval, that is x belonging to this interval minus pi by 4 to pi by 4. So we can also write it like this: x is greater than minus pi by 4 and less than pi by 4, right? Now here we have pi by 4 plus x, that is sine of pi by 4 plus x. So let us add pi by 4 throughout this inequality, so that here we get x plus pi by 4. So adding pi by 4 throughout, we have minus pi by 4, then we add pi by 4. Here we have pi by 4 plus x, adding pi by 4 throughout, and here we have pi by 4 plus uh, pi by 4, right? So here these two terms get cancelled. Here we have simply pi by 4 plus x, and here pi by 4 plus pi by 4 is 2 pi by 4, that is equal to pi by 2. So here we have pi by 2. So now from this inequality we can conclude that this angle, that is pi by 4 plus x, it lies between 0 and pi by 2. So here we have the quadrants. Here we have 0, here we have pi by 2, here we have pi, 3 pi by 2, and here we have 2 pi. This is the first quadrant, second, third and fourth, right? So what we have done here, x belonging to this interval minus pi by 4 to pi by 4, x is greater than minus pi by 4, less than pi by 4, adding pi by 4 throughout, we have pi by 4 plus x greater than 0, less than pi by 2. So here this angle pi by 4 plus x, it lies between 0 and pi by 2. So our angle pi by 4, it lies somewhere between 0 and pi by 2, that is it lies in the first quadrant, right? And in the first quadrant the sine function is a positive, right? So from the sign convention of trigonometric functions in four quadrants, we know that the sine function is positive in the first quadrant and in the second quadrant, right? So here pi by 4 plus x, that is this angle, lies in the first quadrant. So this term sine of pi by 4 plus x is greater than 0, because this angle lies in the first quadrant, right? So here we can now conclude that our derivative f prime of x is also greater than 0, because square root of 2 is already greater than 0, and sine pi by 4 plus x is greater than 0. So this product is greater than 0, and this is the condition for an increasing function, right? So a function is said to be an increasing function if the derivative is greater than 0 for all x belonging to the domain, and here f prime of x is greater than 0, as pi by 4 plus x is greater than 0 and less than pi by 2. So this proves that this function is an increasing function on this interval. So now consider this problem where we have to prove that the function f of x, which is equal to e raised to 3x, is an increasing function on the set of real numbers. So here we are given the exponential function. So to prove that this function is an increasing function on the set of real numbers, let us first find out the derivative of f of x. So f prime of x is given by d by dx of e raised to 3x, and the derivative of e raised to 3x with respect to x is given by e raised to 3x, and then by chain rule the derivative of 3x is simply 3. So we have 3 times e raised to 3x. So we know that the derivative of e raised to say m times x is given by m times e raised to mx, right? So the derivative is given by 3 times e raised to 3x, and from the definition of exponential function, we know that 3 times e raised to 3x is always going to be greater than 0 for all x belonging to R, right? So the exponential function is always going to be positive, that is e raised to 3x is always going to be greater than 0 for all x belonging to R. So here f prime of x must be greater than 0, because here 3 is positive and e raised to 3x is also a positive quantity for all x belonging to R, because e raised to 3x is greater than 0. So f prime of x is greater than 0 for all x belonging to R. So this proves that this function is an increasing function on R, because we know that a function y is equal to f of x is an increasing function if f prime of x is greater than 0 for all x belonging to the domain, right? So this is how we can prove that the function e raised to 3x is an increasing function on the set of real numbers. So now consider this problem where we have to prove that the function f of x, which is a linear function here, f of x is equal to 5x minus 2, is a strictly increasing function on the set of real numbers, right? So let us now first find out the derivative of f of x. So f prime of x is given by d by dx of 5x minus 2. So here we can now write 5 times the derivative of x, and the derivative of 2 is going to be 0, because it is a constant and the derivative of a constant function is 0. So here we have 5 times 1. The derivative of x with respect to x is 1. The derivative of 2 being a constant is 0. So here we have simply 5. So here we have f prime of x is equal to 5, and from here we can see that the derivative it is independent of x, right? So f prime of x is always going to be greater than 0 for all x belonging to R, because the derivative function is independent of x. And here in the given function we can see that the domain of this function is the set of real numbers, and here the derivative is equal to 5, and 5 is always a positive quantity, that is it is greater than 0. So our derivative f prime of x is also greater than 0 for all x belonging to R. So this shows that this function is strictly increasing function on the set of real numbers. So now consider this problem where we have to prove that this function f of x, which is equal to 2 over x minus 5, is a decreasing function on the set of real numbers where x is not equal to 0. So now if we look at this function, we can easily see that this function is not defined for x is equal to 0, right? So the domain is given by r minus 0, that is x should not be equal to 0, right? Okay, now a function is said to be a decreasing function if the derivative f prime of x is less than 0, or the derivative is negative for all x belonging to the domain, right? So here what we will do, we can find out the derivative. So f prime of x is given by d by dx of 2 over x minus 5. So the first step is to get the derivative of this function. So here we have now a d by dx of 2 over x, then we have minus d by dx of 5. So here we can take 2 outside this derivative operator. So we have 2 and d by dx of 1 over x, which can be written as x raised to minus 1. Here the derivative of 5 is a 0, being a constant, because the derivative of a constant function is 0. And here the derivative of x raised to minus 1 is given by minus 1 over x square, using the power rule. That is the derivative of x raised to n is given by nx n minus 1. So here we have minus 2 over x square, and obviously here x is not equal to 0, right? So the derivative is given by minus 2 over x square, right? Now see here, x square is always going to be greater than 0, because this term, that is x square, is greater than 0, and here 2 is also greater than 0, right? So here we can now write 2 over x square is always going to be greater than 0 for all x belonging to R, except x is not equal to 0, right? But here we have a negative sign due to the derivative. So when 2 over x square is greater than 0, then minus 2 over x square is less than 0 for all x belonging to R, and x is not equal to 0. So minus 2 over x square is less than 0 for all x belonging to R, x is not equal to 0. So here we can now conclude that the derivative is less than 0 for all x belonging to R, x not equal to 0. So this implies that this given function f of x is a decreasing function on R, where x is not equal to 0, because the derivative is less than 0.